In this lesson, we are going to talk about the concepts of displacement, velocity, and second derivative. In this respect, we are going to define two new phrases here. One is called the displacement and the other one is velocity. Both of these, they have a magnitude. For instance, in the case of a displacement is the distance, and also they have a direction, which is going to show in what direction the object is moving away from the origin. Now, if we take the first derivative of the displacement, we are going to derive what we call the velocity, which is the rate of change of displacement. The velocity also has a magnitude, which we call the speed, which doesn't have any sign associated with it, and also it has a direction. The unit of the magnitude of displacement is in meters, and the unit of the magnitude of the velocity is in meters per second. We are going to also define a new term called acceleration, which is the rate of change of the velocity with respect to time. In the case of acceleration, the derivative of the velocity is going to be the second derivative of the displacement. In the first example, we have been given f of x to be 1/3 of x cubed minus x squared minus 3x plus 4. We are supposed to find the second derivative of f at x equal to 2. So again, f is 1/3 x cubed minus x squared minus 3x plus 4. So f prime is going to be 1/3 times 3x squared, because the derivative of x cubed is 3x squared, minus 2x minus 3, which is going to be x squared minus 2x minus 3. The second derivative is going to be exactly the same way. So the second derivative, which we denoted with f double prime, is going to be equal to 2x minus 2. Now f double prime of x, which is 2, is 2x. X is 2 minus 2, which is 4 minus 2, which is going to be 2. Now, if we look at the original equation f of x, and if we plot the graph, roughly, we are going to get a graph like this. You are going to get a graph which looks like this one. This is our f of x. Now let's go ahead and analyze this graph and see how the graph of the derivative of this function, which is going to be the velocity, is going to look like. First, let's look at different sections of the graph. The graph is maximum here at this point, minimum here. Remember that the first derivative is the rate of change or the slope of the graph. When we are at this point or at this point, because the tangent is going to be parallel to x-axis like this, it means that the rate of change is 0. So in our velocity graph, or the first derivative, this point corresponds to this point, and this point corresponds to this point. So these 2 points are going to be our x-intercepts for the first derivative. Now, let's look at this part of the graph. If you imagine a tangent here, which is drawn on the graph, and then draw another tangent and another tangent, first of all, you can see that the tangent lines, they will have a positive slope, and they decrease until they get to the value of 0, which is this point. So this means that this part of the graph is going to correspond to positive y value, which is above the x-axis. So the first part, we are going to have something like this one, which is over the x-axis. Now let's consider the graph from this point, let's call it A, to point B, which corresponds to this point on the first derivative to this point. You can see that if I draw the tangent line here, the tangent is going to have negative slope. It's going to start from 0 at point A, and it's going to increase in magnitude, and then it's going to continue to decrease until it gets to 0 again. And since the slope is going to be negative for these tangent lines, this means that they correspond to negative y values for the first derivative. This means that our graph for the first derivative is going to be negative here. So it's going to be something like this one. Now if you consider the last part of the graph, which is here, you can see that the tangent lines, if I draw it roughly here, you can see that the tangent line, they have positive slopes. They start from 0 at point B and they increase. So this means that this part of the graph on f of x corresponds to positive y values for first derivative. So the corresponding graph for our f prime is going to be something like this one. So this is roughly the graph of first derivative. Now let's see what is the graph of the second derivative, or the acceleration here. Remember, the most important point for the graph is where it changes sign, or the direction. If you look here, the graph changes direction, and at this point the rate of change is 0, which represents 0 slope. So this point corresponds to a point something like this point here for our second derivative. Now if we look at the first derivative graph, which is this part, you can see that our tangent is going to have negative slope, and they are increasing in value. They start with a very, very small slope and they get to 0. So, and the sign of it is negative. So this means that in the second derivative, this part of the graph is going to be under the x-axis because they are negative y value. So it's going to be something like this line here. When we go to the second part of the graph, which is this part, we can see that the slope is positive, starts from 0 at point C, and then it starts increasing. So it corresponds to positive y value, which is over the x-axis. So it's going to be something like this one. So you can see that the second derivative looks like a linear function, which is exactly what we got here. And the first derivative looks like a quadratic, which is what we got here. two new terms that we are going to define here are called scalar quantities and vector quantities. Scalar quantities are quantities that are described only by magnitude, just a number, like speed. There is no direction associated with it, or what we call, there is no vector associated with these quantities. Now, vector quantities, like velocity, these are the quantities that, beside magnitude, they need the direction, which has to be specified. So there is a big difference between velocity and speed. Speed is a scalar quantity. There is no direction associated with that one. But vector quantity, like velocity, it needs a direction at the same time as the magnitude. In this example, we have a construction worker which drops a hammer from a height of 90. The height of the hammer, s in meters after t seconds, is modeled by this equation, where t has to be greater than or equal to 0. The first part of the question says, determine the average velocity of the hammer between 1 and 4 seconds. The average velocity, which I denote with V bar, is going to be S4 minus S1 divided by 4 minus 1. S4 is 90 minus 4.9 times 16 minus S1 minus 90 plus 4.9 times 1 divided by 3. If we evaluate this one, we get negative 24.5 meters per second. The next part of the problem says explain the significance of the sign of your result in part A. Usually in problems like this one, we assign direction and we assign upward direction to be positive and downward direction to be negative. When we get that negative 24.5 meters per second, this specifies that the direction is downward. Or another way of looking at it, because velocity is rate of change of the distance, then we can say that because of the negative, the rate of change is decreasing. The height is decreasing as time passes. The next question says determine the velocity of the hammer at 1 second and 4 seconds. We know that s of t is 90 minus 4.9 t squared. So the velocity v of t is derivative of 90 is 0 minus 2 times 4.9 t, which is minus 9.8 t. So the velocity at time t equal to 1 is 9.8 meters per second, and the velocity at 4 is minus 9.8 times 4, which is equal to negative 39.2 meters per second. The next part of the question says, when will the hammer hit the ground? We know that s of t is equal to 90 minus 4.9 t squared. When it hits the ground, s of t is 0, the distance. So from here I get 4.9 t squared is equal to 90, or t squared is 90 over 4.9. If I take the square root of this, I get t is about plus or minus 4.29 seconds. But since time has to be positive, so the answer is t is approximately 4.3 seconds. It takes 4.3 seconds to hit the ground. The next question says, determine the impact velocity of the hammer. We know that the velocity, we found that it's equal to negative 9.8 t. This is what we found previously. Now we say that v of 4.3 is negative 9.8 times 4.3, which is approximately 42.14 meters per second. The next part of the question says, determine the acceleration function. What do you notice, and interpret its meaning for this situation. We know that the velocity is minus 9.8 t. Acceleration, a of t, is v prime of t, which is negative 9.8. If I find the derivative of this one, it's negative 9.8. The first thing is that you can see that the acceleration is constant. It doesn't depend on time, and it is negative. Remember that upward we denote with positive, downward we denote with negative. So the acceleration is downward, so it's negative, and it's constant as long as the air resistance is ignored. When dealing with an object which has a displacement, there are two things that we have to remember. First of all, we said that the velocity is the first derivative of displacement function, and the acceleration is the first derivative of the velocity function, or the second derivative of displacement. At any time t, when the velocity and an acceleration, the product is greater than 0, then it means that the object is speeding up. And when the product of velocity and acceleration is negative, then the object is slowing down. To fully understand the concept that why the product of velocity acceleration, if it's greater than 0, the object is speeding up, let's consider a couple of table of values here. Let's say we have the following scenario. At time 0, 1, 2, the velocity is negative 5, negative 10, negative 18. Remember that the negative in front of the velocity just tells you the direction of the velocity. If we assume that the up direction is positive, the down direction is negative, then the velocity is pointing downward. But if you look at the absolute value of the velocity, which is 5, 10, 18, it is obvious that the object is speeding up. In this case, you can see that the velocity is less than 0 here. And if we look at the acceleration here, acceleration is rate of change or the slope of the velocity. So for the first two, we can see that it's negative 10 minus 5, negative 10 minus 5 over 1 minus 0, which is going to give us negative 10 plus 5 is negative 5 over 1 is negative 5. If we find the slope here, we get negative 18 minus 10 over 2 minus 1, which is going to be negative 8. You can see that the acceleration is also negative, and previously we said that the object is speeding up. So velocity is negative, acceleration negative, and the object is speeding up. That's the first scenario. The next scenario, let's look at this table of values. Let's say 0, 1, 2, 5, 10, 18. Again, you can see that the object is speeding up because 5 to 10 and 10 to 18. So we say that this is another case of speeding up, but this time the velocity is greater than 0. Now, the same way we are going to find the acceleration here. The first one is 10 minus 5 divided by 1 minus 0, which is going to give us 5. The next one is 18 minus 10 divided by 2 minus 1, which is 8. You can see the acceleration is also positive. And again, the same case. The object is speeding up. So this one, these two are examples of the first case. The acceleration and velocity, they are in the same direction and the object is speeding up. Now let's consider different cases. Let's say we have the following scenario. As you can see, the acceleration is greater than 0, but the object is slowing down because we go from 8 to 5 to 0, so it's slowing down. Again, if we find the rate of change or the slope of the velocity, we get 5 minus 8 over 1 minus 0 give us negative 3. The next case, 0 minus 5 divided by 2 minus 1 gives us negative 5 over 1, which is negative 5. And you can see that the acceleration is negative. This is the case that the velocity and the acceleration are of different signs and the object is slowing down. The last case is going to be when the velocity is negative, let's say negative 8, negative 5, and 0. Negative only represents the direction of the velocity, which is downward. If we assume upward is positive, again, the object is slowing down because 8, 5 to 0, it's slowing down. And the velocity is less than 0. Again, if we find the acceleration here, we get negative 5 minus 8 over 1 minus 0 is 1, which is going to give us 3, and 0 minus 5 over 2 minus 1, which is 1, so 5 over 1 is 5. You can see the acceleration is positive, and these are opposite signs, and the object is slowing down. So these are examples of why these two concepts are correct. In the next example, we have the graph of the position of a particle moving along a straight line, given by the graph here. We are supposed to sketch the graph of the velocity of acceleration functions. So if I have another coordinate system here, which is t, and this is going to be the velocity, you can see that the velocity here and the velocity here are 0, which corresponds to these points here. Because the slope of the graph at these points is a horizontal line, and the slope of a horizontal line is 0. Now, if we draw the tangent to the graph at these points, you can see that the tangent is positive here. The slope of the tangent is positive, and it starts with some value here at origin, and it gets closer and closer to 0. Since the slope of the tangent is positive, this means that this part of the graph on the displacement graph is going to correspond to positive y values. So it's going to be something like this. Now, if we look at the part of the graph from here to here, you can see that the tangent is going to have a negative slope So it corresponds to negative values of the velocity graph. And the negative values are all going to be under the t axis. Now we are going to start with a negative slope here, and we're going to continue going down. Somewhere in middle here, the slope is going to change sign and get closer and closer to 0. So this one represents something like a vertex, which is where the velocity is going to start going toward 0. Now if we look at this part of the graph, again the same idea. If we draw the tangents here, you can see that the tangent is going to have a positive slope, which corresponds to the positive values in the velocity graph, which is going to be above the t axis. So it's going to be something like this one. So this is approximately how the velocity graph looks like when we have given the displacement graph. Now we are going to find how the acceleration graph is going to look like. Now for the acceleration graph, we again look at this time the velocity graph. This is our velocity graph. If we draw again the tangent here, you can see the tangent is going to have negative values up to this point. At this point, our tangent is going to have a slope equal to 0 because the tangent is going to be horizontal. So this point corresponds to this one on our acceleration graph. This part, because the slope is negative, corresponds to values of a under the t-axis, which is going to be something like this one. And this part, as you can see, the tangent is going to have a positive slope, so it's going to correspond to positive a values, which is going to be a line like this one. Now we are going to check the graph and decide in which interval the object is speeding up or slowing down. Remember what we said before, that when a of t times v of t is greater than 0, then it's going to speed up, and when at times vt is less than 0, then it's going to slow down. Now let's divide the intervals, as I have indicated here, from time 0 to 2, 4, 6, and over 6. Now when we look at the interval 0 to 2, you can see that the velocity, which is here, is going to be positive, but at the same time the acceleration is negative. So in this interval between 0 and 2, velocity times acceleration is going to give us a negative value. So this means that the object is slowing down. Now from 2 to 4, we see that the velocity is here, which is negative, and the acceleration also from 2 to 4. If I draw the line here, you can see that the acceleration here is negative 2. So negative times negative gives you positive. So this means that the object is speeding up. From 4 to 6, we can see that the velocity is negative and the acceleration is positive. It's here. So acceleration times velocity is going to give us a sign of negative times positive is negative, so it means that the object is slowing down. And last, for time greater than 6, you can see that the velocity is positive and the acceleration is also positive, so positive times positive gives us positive. This means that the object is speeding up. In the last example, we have a graph as shown here, which is divided into different segments. And what we have to do is to describe the slope of the graph in terms of positive, negative, increasing, decreasing over the interval between consecutive points. And for each interval, we have to determine the sign of the velocity and acceleration by considering the slope of the graph. Let's consider from 0 to a. In this interval, 0 to a, which is shown here, if we draw the tangent, you can see that the slope is positive, and also the slope is increasing. The velocity is going to be positive because the slope is positive, and if we look at the interval 0 to a, we can see that the velocity is increasing, so this means the acceleration is positive. So this is for 0 to a. For a to b, for this interval, you can see that the tangent is going to have again a positive slope, but as you can see, the tangent is going to get to point B, which is going to be the horizontal, which is slope 0. So this means that the slope is decreasing. Now, since the slope is positive, the velocity is positive, but now since the velocity is decreasing when it gets to a point when it's horizontal, which is 0, this means that the acceleration has to be negative to work against the velocity. Now let us consider from B to C. From B to C, we start with the tangent line, which is horizontal, so the slope is 0, and the tangent lines are going to have negative slopes, and since they have negative slope and we start from slope 0, this means that the slope is decreasing. Now since we start with slope 0, and although we are going to have negative slopes, but the velocity, which at point B is 0, is going to increase. Since the velocity is negative here because the slope is negative, this means that the acceleration has to be also negative. This means that the object is getting faster. Now the next part that we are going to look at is C to D. Again, if we draw the slopes here, we can see that the slope is negative, and since we are getting closer and closer at point D to a horizontal line, this means that the slope is increasing, because remember that at C you have a negative slope, at point D we almost have a 0 slope because the line DE is horizontal. So this means that the slope is increasing. Now since the slope is negative, then it means that the velocity is negative, and since at point C our velocity is other than 0, some number, and when we get to point D we know that the velocity is 0 because DE is a horizontal line. This means that our speed is getting slower, getting lower and lower, this means that the acceleration has to be positive because the velocity is negative from C to D. And the acceleration has to be the opposite sign, which is positive. Now from D to E, we know that this is a horizontal line, so the slope is 0, and the velocity is going to be 0, and acceleration is going to be also 0. From point E to F, if we draw the tangent, you can see that the tangent is going to have a negative slope. And remember that you start from a horizontal tangent at point E, and then we are going to get further and further closer to a vertical line. Then it means that the tangent is decreasing because that vertical line is going to be negative infinity. Now the velocity, because the slope is negative, is going to be negative here from E to F. And also the acceleration, since at E the velocity is 0 and at F it has a velocity other than 0, then it means that it's speeding up. So this means the acceleration has to have the same sign as the velocity, and velocity was negative, so acceleration is going to be also negative.